Alright, let's take a look at section 3.4, library of functions, and then at the end we're going to take a look at piecewise defined functions. So, the library of functions is our first objective. We're going to graph them and just make sure that we know all of them, how they're all going to look. So the first one we're going to take a look at is the square root function, and we're going to assume that it's just the positive square root as listed here. So it's going to look like this. The square root of 0 is 0, square root of 1 is 1, the square root of 4 is 2, square root of 9 is 3, so we get our first 4 points, and it'll start to bend, curve like this. It'll flatten out. The bigger x gets, then y gets bigger, but not quite as big. Domain and range are going to be all positive, non-negative real numbers, so we're moving to the right and we're moving up, so x is greater than 0 and y is greater than 0. We can say that for both of these. So domain x is greater than or equal to 0, and range y is greater than or equal to 0. Alright, so the x-intercept and the y-intercept are both at 0 right here, and the function's neither even nor odd. It's only existing in the first quadrant, and we're increasing from 0 to infinity. We do have a minimum of 0 at x equals 0. So that's our first one, square root function. Let's grab our second one. How about the cube root function? So this will exist in quadrants 1 and 3 because we can have a positive and negative cube root. And so the domain and range are going to be all real numbers. The x-intercept and the y-intercept is the origin again, here 0, 0. We have symmetry with respect to the origin, so we are odd, and we're increasing from negative infinity to positive infinity. So we're always increasing, always going uphill here. We do not have a local minimum or maximum since we're increasing and decreasing on both ends. Alright, so pause the video if you need to get all that down for the cube root function, and then we're moving on to the absolute value function. Alright, so the absolute value, remember anything negative, negative 3, we make positive, positive 3. But then positive 3 would just be itself positive 3. So it ends up looking like this as a v. Domain is going to be all real numbers, but the range is y is greater than 0. We're only going to be above the x-axis. The intercept here is the origin again, 0, 0. And we are symmetric with respect to the y-axis, so we are even. We're decreasing from negative infinity to 0, going downhill here, but then we're going uphill here, so we're increasing from 0 to infinity. And then we do have a local minimum right here of 0 at x equals 0. So our third function in the library of functions is the absolute value function. Alright, so we're going to add a few more in. We won't go into all the details of these, but you should be able to recognize them and graph them when you see them. So f of x equals b, any number, f of x equals 5, f of x equals 10. We know that's the horizontal line going across here. Intercept, y-intercept at 0, b. Identity function, y equals x, or f of x equals x, is the line going up here with the slope of 1. We can add in the square function, y equals x squared. That's our parabola. We've seen that before. Our cube function, f of x equals x cubed, this bends here when the x values are between negative 1 and 1 when they're fractions. So we'll slow down our growth, and then once we get bigger than 1, we start taking off again. Square root function we've seen. Cube root function we've seen. We haven't seen, well, we've seen this before, but not in this video. The reciprocal function, 1 over x, is this curve that's being sucked towards the x-axis and the y-axis in quadrant 1 and in quadrant 3. No intercepts for this. It doesn't cross either the x or the y-axis. And we've seen the absolute value function. So that brings us to the greatest integer function. This is also known as the step function, because it looks like a step of stairs. So it's a rounding down function. We take whatever x value we have and we round down. So if you're negative 1, the y is negative 1. But if you're negative a half, we go back to negative 1. Negative a quarter, round down to negative 1. 0 gets to be 0, but 1 quarter, round it back down to 0. 1 half, round it back down to 0. 3 quarters, round it back down to 0. We don't have the y value change to 1 until x is 1, and so that looks like this. We're at a quarter, we're at a half, we're at 3 quarters. Not until we hit x of 1 do we jump up to a y value of 1. Same thing here, 1.1, 1.2, 1.3, 1.4, you get up to 1.9, still here, 2, jump up to the next y value, so y is 2 here. Alright, so it will look like a set of stairs going up, step function, also the greatest integer function. And when we graph it, it will look like this, and it could look like this over here if you have connected mode on, and it might do that. It didn't on mine. Some of yours it will. You'll have these connecting lines, right? But it's really looking like this. Alright, so try problems 9 through 16. Those will be problems based on all of the functions in our library. Alright, second and last objective for this video is to graph piecewise defined functions. So sometimes we want to do functions that do one thing in one part of the graph, something else in another part of the graph. So I've put this into the graphing calculator. There we are. And so if we remember from the last video that we can set some restrictions on what the x is going to do here. So we want to graph x squared as long as x is less than 0, and that's what it says here as well. So this is a piecewise function because we're graphing in pieces, 3 different pieces here. When x is 0, I want y to be 2, and when x is greater than 0, I want it to be x plus 2. So let's go ahead and graph this, see what it looks like, and it graphs just like this. So here's the left side of a parabola. It doesn't keep going up though because we've said we only want to draw that graph if x is less than 0. When x is 0, y is 2, and then it jumps right onto this line here when we're bigger than 0, x plus 2. Alright, so really quickly here, let's go back to the question here. Find f of negative 2. Alright, so when x is negative 2, we're going to be here because x is less than 0. So f of negative 2, we're going to say negative 2 squared, which is 4. And we're going to be in that portion, that piece, right, of the function. How about f of 0? That one is predefined. When x is 0, automatically our answer is 2. And how about when when x is 3, then x is greater than 0, so we're going to say 3 plus 2, and we'll get an answer of 5. Alright, we've already graphed it, but let's go back to the graph to see if f is continuous. Is it continuous? Definitely not, because it's not one smooth graph. We would have to jump our pencil up here if we were graphing by hand. So continuous means we would have one nice continuous line. We clearly don't because we have a break in our line right here. So it's not continuous. What is the domain? The domain, what x values could we put in? We can put negatives in, we can put 0 in, we can put positives in. This domain is all real numbers. And what's the range? So we can see here that the range is we're going to be above the x-axis. And here, do we ever touch the y values between 0 and 2? Not on these two functions, but we do on the parabola coming down. So it is, the range is going to be y is greater than or equal to 0. All right, try problem 29. Okay, last example here to try. Let's see the word problem here. So we have an electric company that charges you $7.58 just for showing up, 8.275 cents per kilowatt hour for the first 400 kilowatt hours, and then 6.208 per kilowatt hour for every kilowatt over that, over the 400. So let's see what the charge would be for 300 kilowatt hours. So for the first part, part A, it would be $7.58. You have to pay that regardless. Plus, you have to pay 0.08275 times 300 kilowatts. All right, let's grab our calculator, compute that. So 7.58 plus 0.08275 times the 300, and we get $32.41. We'll round it there because we're dealing with the money. All right, how about 700 kilowatts in a month? All right, so this is a little bit different here because this is 400 kilowatts at the 8-cent rate plus another 300 kilowatts at the 6-cent rate. So let's see what we've got here. We've got 7.58 plus 0.8275 times the first 400 plus, then we have the second rate, 0.06208 times the last 300 hours. All right, let's go ahead and plug this in, see what we get. So that's the first 400 hours. And I'm going to just hit enter here just to calculate what that is, and then add in the additional 300 hours at the 6-cent rate, 0.6208. All right, so that's 18,624, so we'll add those together, plus the 40.68. And so it's $59.30. Okay, so now the reason that I calculated this first amount, the 4068, the first 400 hours, is that how can we develop a model relating the monthly charge for kilowatt hours used? And the way we're going to do that is to come up with a piecewise function. So let me clear off all this, and let's see if we can do this. So the function of x is going to be given by two pieces. We're going to have one function for the first 400 hours. So that's pretty straightforward. That's 758 plus 0.08275 x, but that is as long as x is less than or equal to 400. All right. Then we need to say, okay, what happens if we go over that? So then we know if we've gone over that, we're paying at least $40.68. Because that's how much it would be to pay the first 400 hours. That's what we computed here. All right, so then how much do we have to add on? So we're going to have to add on the new rate of 6 cents, 0.6208. Now be careful here because we don't want to use x, because we only want, if we're going for the 401st hour, we don't want to times all 400 hours. We only want to times the 1 hour that's over the first 400. So we need to say x minus the first 400 so we don't get double billed. And that's if x is greater than 400. And there you go. That would be your piecewise function. All right, and that is that. So there's no problem trying on those. Just know how to do the word problem based on this example. And any questions, make sure we're asking them in class. Good luck with those problems.